Thank you for joining us for our February chromatography webinar, utilizing ELSD and MS as secondary detectors for PrEP HPLC and Flash Chromatography. We have a chat and QA functions available for you to use during this presentation. This webinar will be recorded and a video will be made available. Our presenter today is Josh Lovell, Applications Chemist.
Thanks, Natalie. So today, the outline of what I'll be discussing. Begin with a background and comparison of the different available methods of detection for both Flash and PrEP HPLC systems. Include our UV-Vis or UV-Vis detectors, ELSD, mass spec, pure ion module, or alternate external detector methods. We're going to also kind of focus on getting the most from UV or UV-Vis technique, choosing a detector based on your application or compound class. We're going to go into the benefits of an integrated ELSD solution and how you can increasing efficiency and gaining more information with the pure ion mass spec module. So to begin, so what detection options are available and useful for purification? So available methods of detection on all of our systems include UV or UV-Vis detectors, the UV from 200 to 400 nanometer wavelength, and the UV-Vis from 200 to 800 nanometer wavelength. So you get the extended range with the UV-Vis. All of our systems offer an integrated ELSD option. Within the system, it also obviously integrates well with the PeakTrak software. We also have a pure ion mass spectrometer module that can be added to any of the systems. And then all of the systems except the NextGen offer external detector input and some examples, and analog input. Some examples of where customers have used these is a radiochemical detector, fluorescence, or refractive index as an alternative detector for some unique applications. So we won't go into any more details with those, but those are available. So beginning with UV and UV-Vis detection, it's a non-destructive technique. There's two configurations, the UV or the UV-Vis module with the wavelengths I mentioned before. Both of them are PDA detectors. It requires a chromophore for detection, so you need to have some sort of UV absorbance within the molecule. Systems without baseline correction limits your solvent choices for UV. So if you have a solvent that is also absorbing, then you get competition between that and your compounds, and it can overwhelm what your compound chromophore, so you're not able to see it with the solvent background. Our NextGen series does offer a baseline correction feature that allows you to use UV absorbing solvents. You can choose to trigger collection or monitor up to 2 wavelengths, and the entire UV spectrum is saved throughout the chromatogram, so you can go and look at the UV spectrum and see maybe if there's a better peak, and we'll discuss that a little bit later. And then all of our systems do offer an all-wavelength detection feature utilizing the UV or UV-Vis, and we'll discuss that in a little more detail later too. The ELS detection here, kind of discussion of how it works. So we've got 2 diagrams there on the side to kind of visualize the process. You have your column eluent coming in through the nebulizer with a carrier gas to help form the droplets. The nebulizer helps spray the compound in the mobile phase into droplets. And then you have a drip tube there, which is the long portion there where your solvent begins to evaporate and then leave the drip tube while your particles remain continuing down the drip tube until they encounter the light source and sensor, and then we can measure the light scattering of the particles there. It's a great technique for semi-volatile and non-volatile particles. As we're evaporating solvent, if you have volatile compounds, that they would also evaporate, and then you wouldn't be able to detect them. So that would be the one downside with ELSD. With mass spec detection, we offer 2 options: your electrospray ionization, This is an ionization process that uses electric fields to generate charged droplets and then ions for analysis. And the solvents kind of drift, solvent vapor evaporates away. The APCI probe is another option. This is a chemical ionization process where the solvent actually acts as a chemical ionization reagent to ionize the sample. So this is a destructive technique, so you do lose a little bit of sample via this method, but it's very sensitive, so it requires very little sample. So overall, there's negligible loss to the mass spec. And your compounds must ionize well to be detected. So if you have difficulty ionizing your compounds, then you're going to have difficulties detecting them via the mass spec. So the first section I want to focus on is kind of getting the most from your UV and UV-Vis methods of detection. If you can maximize using the UV and UV-Vis, you can avoid using destructive techniques like the ELSD and mass spec. And it's also a little bit easier to use. So one of the features that's available on our NextGen series of lines is the baseline correction feature. What this does is it enables a short run, pre-run gradient to measure baseline absorbance and allows the system to subtract baseline from the run. This expands the detection abilities across all the wavelengths, and you're not limited by a solvent UV cutoff. And it allows other solvent alternatives to be used that you traditionally haven't been used in chromatography before because of their conflicting UV spectrums. This opens up greener solvent alternatives as opposed to the traditional solvents we use. And then you can also use solvents that maybe exhibit different selectivities for more efficient separations. So if you're interested in enabling this feature, you can do so in the method editor on the NextGen. And if you click on the details button next to the wavelength, you can select baseline correction, and it will enable it for all wavelengths. Some examples of how you could baseline correction can be utilized and add to the toolbox of your purification toolbox. Here's an example of separating two compounds using hexane ethyl acetate at 250 nanometers, which ethyl acetate absorbs at. And so you can see the baseline drifting upwards until it saturates the detector, and you're not able to really see the second compound at all. You're able to see the first compound, but the second compound basically gets completely washed out. If we enable the baseline correction, though, you can see that even monitoring at 215 there, the purple wavelength, it mitigates all the baseline drift upwards with the solvent, and you're able to get clean resolution between your peaks there. So we're able to see the sample still, even though the ethyl acetate is blocking it out, or drifting upwards with it, sorry. Another example is actually changing to a different solvent. So acetone is found a good use as an alternative solvent when we use the baseline feature, a baseline correction feature. With acetone, without the baseline correction, you can see the chromatogram on the left there. This is a single compound, but you can see the baseline drift towards the end there. However, when we do the baseline correction with acetone as a solvent, you can see the peak resolves a lot more cleanly. It doesn't have the acetone fragment or the acetone remnants in the spectra causing the baseline drift. So it helps clean up your chromatogram there. Additional features to optimize ways to optimize your UV and UV-Vis settings for maximized recovery. If you're using UV-Vis and the compound has a more strongly absorbing wavelength outside the UV range, you could choose a better wavelength for detection and get better sensitivity that way, particularly if it doesn't conflict with your solvent. So you're able to increase your sensitivity that way. Deviation from the optimal wavelength for a compound can significantly impact your detection and fraction collection, triggering and sample recovery. To find the optimal wavelength for detection of your compound, you can use a previous UV spectral data, and you need to be aware of any solvent, some solvatochromatic effects due to the gradient as the spectrum changes as we change the solvent composition throughout a gradient. Another way to do this, you can actually use the features within PeakTrak to look at your UV-Vis spectral data, particularly if you're using the ACCQPrep and doing small-scale scouting runs before you're before upscaling to a larger amount. You can look at the click on the UV or UV-Vis spectrum and look at the actual spectrum and change your wavelength to optimize it for detection at that point in your gradient. You can also do this with the NextGen. You can use it, but it's probably not as useful if you're doing a kind of one and done purification. But if you're scaling up, it's a useful tool. Or if you're doing multiple runs, you can improve future separations based upon what you observe for the first run. The nice thing about this is as it's monitoring as the solvent gradient is progressing, you're minimizing the solvatochromatic effects that's kind of inherent with gradient elution. Because the solvent's going to be coming out under similar solvent conditions as what the UV spectra is already showing. Some further options you guys can use to enhance your sample recovery by changing your detection options. In the method editor, you can adjust your threshold and slope-based fraction collection trigger settings. This would be true for UV, UV-Vis, ELSD, mass spec. Any detector, you can change the slope-based or threshold-based settings for that. You can choose to monitor multiple single wavelength. So you can set wavelength 1, wavelength 2, and monitor 2 different wavelengths if you're looking at multiple compounds. Another feature on all of the systems that's offered is our all-wavelength detection feature. And so this is an example of 3 compounds that kind of have similar properties, so they have similar spectral properties also. And if you're monitoring at 254, at just 254, you're not able to distinguish between the 3 different peaks because they all have overlapping absorbance at 254. But if you expand and use the all wavelength detection also found in the method editor, and select the wavelength range. So in this case, it's 200 to 400. And in A, B, and C, you can see the slightly different entire spectral properties from 200 to 400 for these compounds. You can see the difference and differentiate between peaks A, B, and C there, so that where we weren't able to see a difference at the beginning of the elution now looks like it's its own peak. So we weren't able to observe compound A using 254, but going from 200 to 400 and using all wavelength, we're able to see that there's 3 compounds coming out there. So it's a useful feature that way. Another way that you can use this feature is you can use it to compensate for drifting baseline from solvent absorbance. So if you don't have baseline correction, you don't have a NextGen, if you have an older generation RF or the EasyPrep or ACCUPrep, you could compensate for drifting baseline from solvent absorbance by using the all wavelength detection. So in this case, we separated out glucose pentacetate. And you can see with the drifting baseline, it's going to cause some errors with the fraction collection because it's dropping down at the end as you decrease the concentration of DCM. But with the all wavelength collection enabled, we're able to basically have a nice baseline there. And the third way that you could benefit from all wavelength detection is that you can separate peaks of closely eluting compounds that saturate a UV detector at a given wavelength. So in this example, we have 2 compounds that are very strong UV absorbers at 207, and so the peaks kind of coalesce there when we're looking at the 207 nanometer wavelength. But with all wavelength detection, we can see a definitive change in compounds and trigger fraction collection based upon that, so we can get more pure sample instead of getting one fraction of the coalesced peak. So That's an additional feature that you can take advantage of to improve your UV and UV-Vis collection settings. So finally, next we want to discuss ELSD as a method of detection, and I'm going to kind of go over 3 different areas here. I'm going to discuss the application and compound classes that traditionally utilize ELSD, the benefits of our integrated ELSD systems in both our flash and our prep systems, and then what ELSD settings you can change and optimize depending on your needs. So to begin with, we're going to discuss some compound classes and applications where ELSD kind of thrives. ELSD is considered a universal detector. They can detect compounds without chromophores as long as they are semi or non-volatile. If they're a volatile compound, that's the only class of compounds that you can't detect via ELSD. This offers more uniform sensitivity of detection, as you're not having the problem of different absorbances at different wavelengths for the compound. So a particle is a particle, and it's going to cause a signal when it gets to the ELSD detector, versus I'm monitoring at a certain wavelength, and if I'm away from my optimal wavelength, and my sensitivity is going to be decreased, or maybe a chromophore isn't as strong as another chromophore. So I may have the same concentration of compounds, but one chromophore is stronger, so it appears to be more sensitive to detection. Compounds that are non or weakly absorbing via UV or UV-Vis would stand a greater ability of detection using ELSD. This would increase your fraction collection accuracy and recovery. And the limitations, I point out this is a destructive detection technique, not destruction, destructive destruction technique. Apologies for the typo. Where you will lose a little bit of your sample to the ELSD for detection. This is usually less than 5%, or this is less than 5% and usually less than 1%, especially at higher flow rates. So on the prep system. So you need to avoid non-volatile mobile phases and/or additives. So you can't use any mineral acids or bases, because those are going to come through the ELSD and be detected. Phosphate buffers are a no-no. You are able to use TFA, ammonium formate, ammonium acetate, acetic acid, ammonium carbonate, or ammonium hydroxide, though, without issue. And you're not going to be able to detect any volatile compounds. So that would be the limitations of the ELSD, but it does offer a nice alternative to UV and UV-Vis for compounds that you aren't able to detect that way. So kind of a survey of different applications of ELSD and compounds that you see in analytical HPLC, and also prep and flash. The purification and identification of natural products, particularly those with unknown properties. So maybe you don't know if this compound has a chromophore, so you're able to detect that via ELSD and detect that there's a compound eluting at that point. Small molecules without chromophores are great as long as they're non-volatile. Polymers, purification polymers, lipids and fatty acids, carbohydrates that usually are invisible via UV-Vis, UV or UV-Vis, unless a chromophore is actually attached to the molecule. So we're going to go over some examples of where we've used ELSD when compounds are undetectable using UV. So this is on our flash system here. We're trying to purify cholesterol and para-aminobenzoic acid. And you can see the chromatogram here. The cholesterol gives us an ELSD signal, but it doesn't give us a UV signal at 254. The para-aminobenzoic acid gives us a signal in both via both detectors. So you can see the advantage of the ELSD for detecting the cholesterol, which would have not even shown up in the UV spectra of the chromatogram, even though there's a compound eluting out. Another example is in the synthesis of 2,3,0 isopropylidine deribofuran furanose. In this case, you look at the UV spectrum and you just see baseline here. This compound has no UV absorbance. We would trigger no fraction collection. If it was eluting, we would have no idea looking at the UV spectra. But if we look at the ELSD, we do get a very strong signal for the first peak, and we're actually able to get 3 different fractions there and recover 821 milligrams of the sample. So this is just from a crude synthetic mixture on our flash system. So you can see the benefit of having the ELSD when you have no UV chromophore to detect in the UV spectrum. So another example here is in the purification of tocopherols. So these are very weakly UV absorbing. You can see the absorbance. You can see some UV absorbance, but it's less than probably 0.02 on the flash system. You can actually detect it a little bit. Even all-wavelength doesn't help out. It helps out a little bit for one of the compounds, which offers something you could change from changing from the 280, but the all-wavelength detection, or sorry, the 280 nanometer doesn't really offer you any value. This improves your sample recovery due to increased sensitivity of the ELSD over the UV, and you can actually see the overlapping fractions there of where the UV would have collected versus what fraction the ELSD would have collected. And so the ELSD actually expands the fraction cutting range because of its increased sensitivity, and you're going to be recovering more sample because of that. Finally, the ELSD does allow you to use an alternative solvent that maybe interferes with UV signal, and in the second graph there, using acetone as a solvent, you can see at 280, this obviously has baseline drift, but with all-wavelength detection and the ELSD, we're actually able to detect it. So just another way that you can increase the tools in your, the tools or choices that you can use for solvents by changing your detector or using an additional detector. So the next portion here, I want to discuss the benefits of an integrated ELSD solution versus just adding an external ELSD. So our integrated solution for the flash system and the EasyPrep hybrid system uses an active splitter pump to adjust to different flow rates. This allows for a seamless interaction between the detector and the software. You're able to adjust ELSD settings during the run, and we'll talk about that a little bit later. There's a dynamic gain adjustment in the PeakTrak method editor for difficult to detect compounds, so we can change from a normal ELSD setting to a high sensitivity ELSD setting that increases the gain. The software obviously monitors for any issues with the ELSD. Maybe you ran out of gas for the ELSD, or the drift tube and the spray chamber aren't to the proper temperature. And so those kinds of issues are going to pop up and say, hey, we need to wait for it to get to temperature before we go. So you wouldn't see those issues or see those problems pop up if you weren't using an integrated software solution for it. PeakTrak, probably the biggest thing that PeakTrak does is it aligns the ELSD and UV peaks to maximize sample recovery and accurate fraction collection. And obviously the gain of the smaller instrument footprint compared to an external ELSD option as it's inside the instrument. And what I am really excited to kind of talk about is our PrEP HPL solution for an integrated ELSD option. So we're going to kind of discuss some issues that we encountered and how our solution kind of overcomes them. So one of the big problems with trying to create an integrated ELSD option for the PrEP HPLC is that there's a broad flow rate range. You're going from 1 to over 100 milliliters per minute, depending on your system. And you need to balance peak overlap with your band broadening of the compound in the UV spectra. So we've got three different flow rates here, 5 mils, 30 mils a minute, and 125 mils a minute. And going through a set amount of delay tubing, you can see that at 30 mils a minute, we get pretty good overlap. So we get good peak overlap. The band broadening isn't too bad between the ELSD and the UV. But when you look at the 125 mils a minute, you can see that the ELSD peak's coming out after the UV, which means that you need more delay volume to align the UV and ELSD peaks for accurate peak cutting. You can see at the 5 mils a minute, though, the problem of that at 5 mils a minute is that you get really bad peak broadening in the UV spectra compared to the ELSD spectra. So now you're not getting a peak overlap. Your samples may even start to coalesce and kind of come back together after you separated them. So that's a problem if you go trying to get the correct delay for 30 mils a minute, and then you're sampling at 5 mils a minute. So the additional problem is if the ELSD peak is before the UV peak, we can go ahead and correct that via software delay. So that's not a problem for the 5 mils a minute, but at 125 mils a minute, the ELSD peak is already is too late, and the sample has already reached and passed the fraction collector, so we're not able to collect if it comes out too late. So we'll discuss one other problem with that we observed using the PrEP HPLC, and that's the difference in the viscosity across the gradient profile for different solutions. So most of our reverse phase systems, mobile phase systems, are acetonitrile water, methanol water. And so if you look at the viscosity curves here for acetonitrile methanol, we already know that acetonitrile is going to be less viscous than methanol, but across the gradient from 0 to 100% with water, there's significant change in the viscosity, and there's significant actual difference in the shape there, the viscosity between methanol and acetonitrile. So as the different viscosities change for the different solvent compositions, using a passive splitter, this results in different delay times between the ELSD because the split ratio is actually changing as the viscosity changes, as it's dependent on the pressure. So that's problematic if you're not correcting for, or not aware and not correcting for it. So some other issues with current non-integrated PrEP HPLC solution, ELSD solutions, like I mentioned before, is the broad range of 1 to over 100 mils a minute. PrEP HPLC use of an active splitter pump is prohibitive because of the increased pressure requirements because of the thinner tubing. And the system actually systems are usually set up for a small flow rate range. So if you're usually using a 20 millimeter column, it's probably set up to optimize around 20 mils a minute. If you're using a 30 millimeter column, the diameter column, then it's probably set up to adjust where you have optimal peak overlap around 40 mils a minute or a range around there, and higher for 50 millimeter columns. But for your 4.6 and 10 millimeter columns, you would need to have a different setup for those to maximize the peak overlap for those low flow rates around 1 or 2 mils a minute or 5 mils a minute. And so that would require you to manually change the splitter and delay tubing loops. So that creates an added difficulty in getting the system set up. Software correction is limited to known kind of delay volume and time based upon those delay loops. And that's something you'd have to change when you change the delay loop. And if you forget to change that, then you're going to have problems. And currently, we're not aware of any solutions for the changing viscosity resulting in UV and ELSD misalignment using a passive splitter. So that's going to lead to peak overlap mismatch between the UV and the ELSD, and decreased accuracy in your fraction collection. So our ACCQPrep ELSD, we've come up with a solution that kind of solves a lot of these problems here. And for example here, this is a 4-component test mix here that has compounds that elute throughout a gradient from 0 to 100%. So we have some early eluting compounds, middle eluting compounds, and late eluting compounds. And using ACCQPrep and the PeakTrak software correction, we're able to get overlap at 2 mils a minute on the 4.6 millimeter column, almost perfectly for that chromatogram there. This confirms the accurate alignment of the ELSD and UV signals throughout the gradient. We have minimal band broadening. The peak shape between the ELSD and the UV is very similar. So what you're seeing in the ELSD is also similar to what we're seeing in the UV, which also means what is coming out and dictating fraction collection into your tubes is accurate. We expanded this and we looked at the 10 millimeter at 5 mils a minute here, and you see also good peak overlap. This column was starting to behave a little poorly, but you can still see good peak overlap, even though the compound's starting to tail, but you see it both in the UV and the ELSD. So it's a good example that confirms that what's happening in the ELSD path is the same as what's happening in the UV path, and that what we're collecting is going to be accurate. If we go up to a faster flow rate for the 20 millimeter column, you can see very good peak alignment, good peak shape, and finally at 30 millimeter column, you see the same thing. Good peak alignment, good similar peak shapes between the ELSD and the UV. So this is going to lead to accurate fraction cutting and good sample recovery of the compounds you're trying to isolate. The ACCQPrep ELSD offers peak alignment and overlap between the ELSD and UV at flow rates from 2 to 125 mils a minute. And it does this all automated, so it recognizes what your flow rate is for the run, and then it selects the appropriate passive splitter path. So all of this is internal. It changes to the splitter path that is most useful for the flow rate you're using. One of the advantages of this, and one of the problems it solves, is it minimizes unnecessary band broadening, especially at lower flow rates. This maximizes your UV and ELSD signal overlap with because you're in the optimal delay loop for that flow rate. It also optimizes the split ratio to the ELSD for improved sensitivity at different flow rates, and it also minimizes unnecessary sample loss via the ELSD. So that's really important, that we're not losing an undue amount of sample because we're using the incorrect splitter. PeakTrak further improves the UV ELSD signal overlap by changing, by knowing where you're at in the gradient. So when we looked at the viscosity curve, you could see that 40% methanol water is significantly different than 100% methanol or 100% water. PeakTrak recognizes where you are in the gradient and can adjust for the gradient solvent composition and what the delay should be for that at that time. This maximizes your peak overlap, which leads to more accurate fraction cutting and collection. So the last point I want to make about regarding ELSD is about optimizing their ELSD settings and what you can change. So one of the key things regarding ELSD is that the noise increases with less volatile solvents and modifiers added if you maintain the same temperature. So normal phase usually have more volatile solvents, so you're going to have less noise. As you go towards reverse phase applications or start adding modifiers like TFA or ammonium buffers or formic acid, you can see in this figure on the right here that the average noise increases with those additions. So as far as setting up and choosing parameters for your experiment, you want to try and minimize that noise to maximize your sensitivity. So one of the ways you can do this is we can control the sensitivity in the detection options for the ELSD. We can choose to do high or normal sensitivity. So if you're working with more semi-volatile compounds, then, and maybe in a reverse phase system, then I would choose high sensitivity. If on the prep systems, I would almost always exclusively work in the high sensitivity mode. With the flash systems, you have the kind of the option. If you're using the normal phase solvents, then we could go down to normal sensitivity so that we're not maxing out the detector, and maybe get some selectivity that way. But if it is a more volatile compound, we can increase the sensitivity to high. Some additional changes that you can make. We can adjust the spray chamber temperature and the drift tube temperature. So the default settings are great for non-volatile compounds, and it works well in reverse phase and normal phase. But if you're trying to detect semi-volatile or semi-volatile compounds, then maybe reducing the spray chamber temperature and the drift tube temperature may be something that you may need to do. If you're working with compounds that you know are extremely non-volatile, then you could also increase those temperatures and minimize maybe some of that noise due to solvent effects such as water, acetonite, the reverse phase solvents and modifiers that you're using to decrease the noise coming from those. So changing the spray chamber and drip tube allows more solvent particles to travel to the detector than evaporating out also. So if you're lowering the temperature for reverse phase, you may be getting into some trouble if you go too much lower than the default settings. So so the last section I'd like to talk about today is the mass spec detector as a method of detection. And so we'll be talking about this in kind of 3 different areas here: application, compound classes utilizing mass spec, PeakTrak mass spec integration features, and then examples of mass-directed purification. So compound classes for mass spec. So there's 2 different probes available for our pure ion mass spec: the APCI probe, which is the atmospheric pressure chemical ionization probe, or the electrospray ionization probe. We discussed the differences earlier. The other additional necessary thing is a carrier solvent. So this dilutes your sample to the mass spec and also helps to ionize compounds by a modifier for mass spec detection, particularly if you're using ESI. So this requires solubility with your mobile phase system. So if you're in a reverse phase system, you're probably using methanol acetonitrile. And if you're using ESI, then you're probably also adding like a 0.1% modifier of TFA or formic acid. If you're using a normal phase solvent, some of the obvious choices would be hexane ethyl acetate, but the problem with that in the mass spec is that they do offer a flammability safety hazard. So DCM is a really good choice for normal phase solvents as a carrier solvent without any additional modifier. So how do I choose what probe would be best suited for my compound? So for the ESI probe, it's generally well suited for reverse phase systems. You need to be able to ionize the compound in solution in order to use ESI. So reverse phase solvents allow that. Compounds that are easily charged in solution, like proteins, peptides, oligonucleotides, and any compounds that contain heterocarbons would be good candidates for ESI ionization and being detected. If you choose the APCI probe, you can use reverse phase or normal phase as your chromatography solvent system. Traditionally, this works well for small. What was I going to say? Polar to non-polar compounds. Sorry. Some examples include like polycyclic aromatic hydrocarbons, fatty acids, steroids. So larger non-polar molecules, small and large non-polar molecules would be suitable to APCI. So here's some examples of optimization of ESI mass-directed fractionation, and also kind of from the perspective of doing information-rich purification. So you're also getting information from your purification also. So this is using our combo flash, the solar flash system here, the NextGen. So this is using an extracted ion current. So this is looking at a, this is using a single ion current. So I apologize for the title, that's incorrect. This is using a single ion current on the separation of caffeine and theophylline. So we have the caffeine, this is the mass spectra of the caffeine fraction that we eluded. And you see the structure of caffeine there with a lot of heteroatoms, so it makes sense to use ESI in the positive mode. We use 0.1% formic acid and methanol as a carrier solvent. We set our mass trigger range to 195. The reason we did that, when we did our method development, we were able to actually directly inject into the mass spec and determine which masses would be suitable for detection. In this case, 195, which is the mass of caffeine, was a suitable choice. So we're able to detect based on that. So we're separating it from the theophylline, which is a very similar compound. It's just not methylated at the amine. And we can see the mass spectrum of the theophylline. We only collected on the caffeine mass, but we're still able to look at the entire mass spectra throughout the run there. So you can see how we're able to separate out. These are both UV active, so we could have separated them out via UV, but this does demonstrate the information you can gain from the mass spec as far as looking at fraction purity, and also using the method development feature to determine an ion to mass ion to target. Another example, so this is from a synthesis, and this is using an extracted ion current. And this is also ESI probe in positive mode. In this case, we're separating out the azobenzene byproduct from the reaction from the benzidine desired compound, the green fraction below. So in this case, we're actually looking at a range of masses from 175 to 300. And you can see the increased sensitivity by looking at the mass range there from 175 to 300 for the second peak versus what appears to be the major peak via UV that comes out around 4 CVs, which is actually the byproduct. So this is a good way to use secondary detection and actually see, okay, that's not the mass I'm interested in. The mass of that first peak was around 180, showed 183 as a major component, which doesn't match up with the mass we expect of 217 or the fragment at 185 of the desired material. So structures are confirmed via NMR there, and so this would take advantage of the range there. You can actually see the intensity of the major product better. So even though the azobenzene is a lot stronger UV chromophore. So here's some additional examples. This is using our APCI probe. And so this is for a separation of ergosterol using single ion current. It's our APCI probe. The carrier solvent in this case is 0.1% formic acid and methanol. The mass for ergosterol is 396.3 Daltons. We took advantage of using our ion finder feature on the method development screen by looking at the desired mass and then comparing that to the detected ions or potential detected ions based on fragmentation. So the mass here is 396.3. Ion finder actually suggests using 379 due to loss of water from the fragment. And you can see on the left there we have the ESI spectra and then the APCI, and this compound is not visible via ESI, so we switched the APCI probe in order to detect it, and you can see the detection of the compound there. Additionally, we can take advantage of the post-run feature and look at the mass spectra of each tube. So if you actually click on the tube in the end run screen, it'll pull up the mass spectra for that tube, so you can see which tubes you'd like to combine because they're pure, or keep separate because maybe there's an impurity starting to develop in it. So this is really helpful for combining your fractions and making sure you don't accidentally contaminate a pure fraction. So another example here is the purification of stigmasterol and cholesterol. And again, this is an APCI probe. In this case, though, we're doing a normal phase chromatogram or chromatography here. So the carrier solvent in this case, we switched to DCM. And so we actually don't get separation between the stigmasterol and the cholesterol, so the actual chromatography didn't work out so great. But we can see that what appeared to be a single peak, if you were detecting via multiple masses, we can actually see that there's two masses that are predominant there, and those match up with both of the compounds. We took advantage of the ion finder feature to look at the fragments that were lost due to water. So you can see that there, the stigmasterol mass is 412 Daltons, and it suggested 379, while cholesterol is 386 and suggested 369 is a good fragment to observe. So once again, you can see the overlap of both the mass spectras shows the compound co-eluted. So I want to discuss some examples with our PrEP HPLC systems. In this case, this is for the purification of peptides, and this is using our EasyPrep system. And the purification of a crude peptide here with a molar mass of 1,091.5 Daltons. The visible masses we see in the method development are the mass plus 1 at 1092 Daltons, the mass plus a sodium at 1,114 Daltons, and then the doubly charged mass of the peptide plus 2 at 546 Daltons. And you can see that by collecting over multiple potential ions for this compound, we're able to detect actually two different fractions that are actually the same compound. So it actually expands our range of collection, so you can actually see the mass spec of both these compounds eluting from the chromatogram there. So, and those match up with the peptide that we expect. We did the same thing using our ACCQPrep HPLC system. So I'm not going to go into the details, but you can do the same thing on there. And here's the HPLC, analytical HPLC of that pure fraction. So you can see that is one compound. And finally, the last kind of mass spec feature we want to kind of point out is our terminate on target. So this is really useful as it saves solvent and time, because you can stop your run after you've collected your compound. So with this feature, on all the systems currently, you can select up to 4 different masses to detect on. You can choose to terminate on target for some or all of the masses. So in this example, we decided to terminate on target for this last peak, or sorry, for this first peak that's eluting. So once it detected that this mass came out, it stopped the run and asked if you want to continue or do you want to end the run. This is the same run further progressed. This is collecting on another mass here on the second peak. And once again, it stops after the second peak is collected and says, do you want to stop or continue? Because we've detected the mass that you're interested in already. And then finally, you could actually choose it to terminate on target on multiple peaks, and so it's going to stop after it's collected both masses there. So you can see the mass spectra on both of those traces, and since it terminate on target on both of them, it's going to collect both before it stops. If you had chosen 4 and only 2 had come out, it's going to keep going until it sees 4 or the run ends. So it's a useful feature to help save you some time and solvent if you know what you're looking for, which the mass spec will give you the information to do that. So that's one of the advantages of the mass spec there. So summary for today, summarize what we discussed today. So we described the available methods of detection for all the systems, including UV, UV-Vis, ELSD, and mass spec, and your external detector options that we've seen used. We discussed tips on how to get the most from your UV-Vis detector, revealed the benefits and convenience that an integrated ELSD detector offers. We showed examples of compounds and applications where ELSD or mass spec offered a more suitable detection technique. And finally, we also examined some different features and settings available on PeakTrak to improve purification with different detector options. So just to kind of summarize kind of the equipment that we have available here, we have our NextGen series of flash chromatography systems on the upper left of the screen, our ACCQPrep HPLC system on the bottom left, the EasyPrep hybrid system prep flash system on the upper right, and then our large-scale flash purification system, the Torrent, on the bottom right. All of these can be coupled together with our pure ion mass spec for mass-directed fraction collection. So you can go to our website. You can also download a copy of our guidelines and tactics for flash chromatography, effective organic compound purification. Just go to the website there and then click on Flash Guide, and you should be able to get a PDF copy or a hard copy I sent to you. Upcoming webinars coming up. My colleague Jack Silver is going to be discussing what to do when things go wrong in LC. So it's going to have some LC troubleshooting, not just for Flash or Prep HPLC, but also just kind of his experience in general with analytical LC also. So feel free to join in for that, and I think you'll learn some valuable tips from his experience. So these slides will be available online in addition to a video of the slideshow. You can email us for a copy of the actual PowerPoint presentation. We have any questions regarding the presentation? I don't have any other questions asked at the moment, so feel free to contact me via email if you have further questions regarding any of our products or anything I discussed in the presentation, or in regards to maybe a unique application you may have. We'd love to be able to help offer solutions for your guys' applications. So feel free to reach out to me, joshua.lovell@teledyne.com. And I appreciate you guys taking the time to listen to me today. Thank you.